Okay, so notes for the multiplication rule and the conditional property. So we're going to talk about first the multiplication rule if we have independent events. So it says two events are independent if they do not influence one another. So do not influence each other. Okay? Almost sounds like what? What's the other one that we learned in a previous notes?
Mutually exclusive events.
Almost sounds like mutually exclusive, right? Because what does mutually exclusive mean? Can they happen together or they cannot happen together? Cannot happen together, right? Mutually exclusive means they cannot happen together. Where independent is they do not influence each other. So they're very similar in wording, okay? But depending on if we're using the addition rule or the multiplication rule, differs if we're going to use those vocabulary. So it says the occurrence of one has no effect on the occurrence of other. For example, if you toss a coin twice, so let's say you toss the first coin, you get a heads. If you toss the second coin, are you going to get tails? Nope, it's still a 50-50 chance. So that means they're independent events. Okay? The next example, the gender of each child born to the same mother. Okay, so I had a son first. Okay? Does that guarantee I have that you have a daughter next?
She had no idea what that was about.
Oh.
I went up to the front desk and she was like,
I said Mr. Pfeiffer was supposed to be waiting for you.
oh, at the front? Is he like tall?
Yes.
Okay.
Yes, sorry.
Okay.
Okay, so the gender of your child doesn't affect the gender of the next. So you could think of your siblings, right? Depending on your gender, okay, did that mean that your parents only had that one specific gender or the opposite gender? No, because they are two independent events. And then lastly, trials with replacement. So trials with replacement means, let's say I have a deck of cards. You draw a card from the deck, and then you put the card back in. That would be trial with replacement. Without replacement means I take the card out of the deck and I don't ever put it back in. Okay. Next it says, if A and B are independent events, then the probability that both A and B occur is found using the multiplication rule. That is the same as saying the probability of A and B is equal to the probability of A intersection B, which is equal to the probability of A times the probability of B. So if we have two independent events, the intersection of A and B, all we do is multiply the two properties, or the two probabilities together. Okay. So let's look at an example. It says if I flip a coin, then roll a dice. Okay. What is the probability I flip a head, then roll a 5? So first, if you flip a coin, does that impact the number you get if you roll a dice? No, so these are independent. Okay, and which means we can think of the probabilities of them happening individually. So what's the probability of flipping a head? 50-50, right? Or we would say, how do we write that as a proportion? 1/2. Okay. Then it says roll a 5. What's the probability of rolling a 5? 1/6. So I'm going to say times 1/6, which means the probability of both happening is 1/12, or approximately 0.083. Okay. Example B, we said that the probability of gender is independent, right? So it says, what's the probability that Mrs. G will have 4 girls in a row? Okay, well, what's the probability of having a girl? 1/2. Okay, what's the probability of having another girl? 1/2. The third one? 1/2. The fourth one? 1/2. So we're going to multiply these all together. So 1/2 times 1/2 times 1/2 times 1/2 is 1/16, which is approximately 0.0625. So about a 6% chance of having 4 girls in a row. Okay. C says, I have a standard deck of 52 cards. What is the probability I pull a red card, replace it, shuffle it, then pull a black card? Okay, so this is trial by replacement, which means the probability stays the same. So, thinking of the probability of first a red card, how many red cards are in the deck? 26. Half the deck is red. Okay. Then it says you put the card back, and now you're looking for a black card. So what's the probability of pulling a black card? Still 50%, right? 26 out of 52. So we would multiply these together. When we do that, we get 1/4, or approximately 0.25. Okay, and remember, you have Desmos, so you could take these proportions, put them into Desmos, and they will give you the decimal. Okay, you don't have to try to calculate these by hand. Okay, D says you spin the following spinner 5 times. What is the probability that you land on yellow all 5 times? So, looking at my notes, how many yellows are there? 3. So that means this probability is going to be 3 out of 8. So we're going to write that how many times? 5 times. And then we're multiplying those fractions all together, and we get 0.007. Okay, so that's less than 1% chance. Okay. Any questions on independent events? Okay. Now we have dependent events. Okay. Events are dependent if they, any ideas? What words did we use in the top? They'll influence each other. Influence each other. The occurrence of one affects the occurrence of the other. One example of that would be trials without replacement. So again, if we think about a deck of cards and I tell you to draw one card, okay, find the probability of that, and then we draw another card without replacing it. Where was I? Okay. The cards. So again, if you find the probability the first time, it's going to be 1 out of 52, correct? But if I don't replace that card, how many cards are now in the deck? 51. So that means the next probability is going to be 1 out of 51. And let's say I do that again, then it would be 1 out of 50, and so on and so forth. So it says if A and B are dependent events, the probability that both A and B occur is found by, and then here's the formula, probability of A and B is equal to the probability of A intersection B, which is equal to the probability of A times the probability of B given A has already happened. Okay, so that is what this little bar means. It means given. Okay, so the probability of B given A has happened. Okay, and we're going to write that definition right there. So this is B given A has occurred, or A has happened. Okay. So it says the conditional probability of an event is the probability that one event will happen if it is known that another event has happened. So again, this is a conditional probability because we are using the terminology probability of B given A conditional probability. We can only take the probability if A has happened. If A has not happened, can we find the probability? No. It says we can rearrange the multiplication rule to get a formula for conditional probability. So what I'm writing now is the formula for conditional probability. So we have the probability of A intersection B over the probability of A, okay, is equal to the probability of A times the probability of B given A over the probability of A. Okay. So all they did is they took the probability of the intersection, which we have up here, okay, and they divided it by probability of A. Well, when you plug this in, what happens to both these probabilities of A? They cancel, and so we're only left with the probability of B given A. Okay. Which means the formula for the conditional probability is the probability of B given A is equal to the probability of A intersection B over the probability of A. Okay, this whole thing right here is our conditional probability formula. The next part is like, okay, well, let's see how this makes sense in terms of the Venn diagram, okay? So I know a lot of you struggled a bit on the Venn diagram notes. I just want you to know that you're never going to be asked to draw a Venn diagram, okay? You're not going to really be asked to fill in a Venn diagram. It's more of, can you look at one that already has data in it and make an interpretation from it? Okay, so hopefully that helps some. You're not going to have to fill in tables or anything like that. It's more of like an introduction to another way to think of these formulas. But as long as you have the formulas known, because I believe a lot of the formulas are on the formula chart, so you'll have that formula chart, you won't have to rely so much on Venn diagram. So it says, why does this formula make sense? It says, when you know something has happened, that changes the sample space. So if we know A has already occurred, that becomes your sample space. So A has already occurred. Okay? So I'm going to say this has already happened. Okay? Then for B to occur, it has to occur with A. Well, where's the only part on here that B occurs with A? In the middle. That's this part right here. Okay. So if we compare this to our formula, our conditional probability formula, the probability of B given A is the probability of A intersection B divided by the probability of A. So intersection, that was the green. Probability of A is the pink. Okay, so when you think of that in the Venn diagram occurrence, then if it's B given A or A given B, that means it has to be somewhere in that intersection where they both share. Okay, so let's look at some examples. A says, I have a standard deck of 52 cards. What is the probability of pulling a spade then pulling a 5. Okay? So think, how many spades are in a deck? 13. It's one of the 4 suits. So we write 13 out of 52. Okay? So if we've already pulled a spade, we were successful in that probability. Are there still 52 cards? How many cards are there? 51. Okay, and then how many 5s are in a deck? 4. So we're going to take 13 over 52 times 4 over 51, and that gives us 0.02. Okay. B says, I have a standard deck of 52 cards. What is the probability of pulling a jack and then pulling another jack? Okay, well, how many jacks are in a deck of cards? 4. So we have 4 over 52 for our first one. Well, if we want to have the probability of pulling another jack, if we already pulled 1, is there still 4 in the deck? There's 3 in the deck. And how many cards are in the deck? 51. So not only the bottom, the denominator decreased, but the numerator decreased because we are trying to pull the same card. Okay. So then you multiply those together and you get 0.005. Notice the probabilities of these happening are very, very small. Okay. In the next example, these are typically how your questions are going to look like on a test. Right? They're going to give you a scenario, a table, and then they're going to ask you specifics about the probabilities. So it says, in your statistics class, you're interested in exploring the taste preference of your classmates. You have 2 tastes, sweet and salty. 25 students were asked if they prefer both, only sweet, only salty, or neither. The following 2-way table shows the data. And I believe we did the same one in the Venn diagram notes. Okay. So it says, what is the probability you select someone who likes salty food and then select another person who likes salty food? So those are our 2 events. So let's look at the first one. If we select someone who likes salty food, how many people like salty food? 13. So we would say 13, and how many total people are there? 25. So if you picked one person who likes salty food, can you pick that same person again? No, so that means there's not 13 people. There's now 12 people you can pick from. And then you also removed it from the total, so is there 25 people? No, there's 24 people. So that would be the next probability. You would multiply those 2 proportions together and get the probability of 0.26. Next one says, what is the probability you select someone who does not like sweet food and then select a person who likes sweet food? Okay, so who does not like sweet? How many do not like sweet? 8. So that's 8 out of 25. Okay, and then who likes sweet? How many like sweet? 17, and then that's going to be out of 24 because we already selected one person and we're not putting that person back into the total. So then we multiply those together and we get 0.227. So about a 23% probability. Okay. So now let's look at an example using conditional probability. We are given a data table filled with hair color and eye color. It says if we select a woman and find she has brown hair, what is the probability that she will also have hazel eyes? Okay, so what we're doing here is first we need to set up what this looks like in words. Okay, so this is the probability they have hazel eyes given what? Brown hair. They have brown hair. Okay. So knowing that this is our conditional probability, the formula looks like finding the probability of the intersection, which means the probability that they have both, right? Both hazel eyes and both hazel eyes and brown hair over the probability of what? Of brown hair. It's always going to be that last part over the given. Okay? And when we set it up like in words like this, it makes it a lot easier to find that data on the table. So what's the probability of both? Brown hair and hazel eyes. So brown hair and hazel eyes, that's 29 out of how many? Is it going to be out of the total of just brown hair or the total of the entire population? The entire population. So this is going to be equal to 29 over 313. Okay, that's our first proportion on the top, because that's the probability of both. And then we look at the probability of just brown hair. And how many of them have brown hair? 143 over the population, 313. Okay. If we think back to the properties of fractions, right? If we have a fraction divided by another fraction, that's the same as taking the fraction and multiplying by its, reciprocal. Yes, the reciprocal. Yep, when you flip it, right? The idea here is if you do that, these go away, which means we're only left with 29 over 143, which is 0.203. Do you really need to know, I guess, fractions? No, because what do you have? We have Desmos, right? You could have typed in those two fractions divided by each other, and it would give you 0.203. Okay, let's look at the next one. It says, if we select a woman and find she has brown eyes, what is the probability that she also has black hair? So what probability statement am I writing? Probability of... It's actually going to be opposite. So it's going to be the probability that they have black hair given they have brown eyes. Right? Because we said here, if we select a woman and find she has brown eyes, so she already has brown eyes. So that has to be given, the statement after given. And so we know that this is the same as saying the probability of both divided by the probability of what? Brown eyes. Okay. So what would be the proportion of having black hair and brown eyes? $36 over 313. And then the probability of just having brown eyes? Good, 122 out of 313, which we can simplify that to 36 over 122, which is 0.295. So about a 29% probability or chance that that happens. Okay. Any questions on conditional probability? Okay. This next part, showing independence, I would say out of everything in this notes and the previous notes would be something that would pop up the most on an FRQ. Okay, so showing independence. So it says if we draw two cards with replacement, we know that those events are independent or dependent. With replacement. Independent. So without replacement would be dependent. Okay. However, in real world, it's difficult to determine if two events are independent or dependent. So we have to prove independence using the following formula. So you can use either formula depending on whatever is easiest for the scenario. The first one is that the probability of A intersection B is equal to the probability of A times the probability of B. So if you plug in all those values and you do not get a true statement, then it's not independent. Okay? Or you could prove that the probability of B given A is equal to the probability of B. Okay? Again, if you did not get a true statement, then they would not be independent events. So in these next examples, we need to prove or disprove independence. Okay, so you can use either formula depending on how it's which is easier to show in your problems. So it says below is a two-way table that shows produce and how many packages are purchased based on whether it's fresh or frozen. So A says, are blueberries and fresh independent? Okay, well, in order to prove that, let's go ahead and try the first one, that first formula. So probability of A intersection B is equal to the probability of A times the probability of B. Okay, let's say blueberries is A, fresh is B. Okay, so we need to look at our table and see if we get a true statement. So what's the probability of blueberries and fresh at the same time? 20 over 140. So this is 20 over 140. Oops. 20 over 140 is equal to, and then we look at just the probability of blueberries. 56 over 140, and then the probability of just fresh. 50 over 140, okay? And then we have to see if these statements are equal. Well, 20 over 140 is 0.143, and if I multiply these two proportions out, I get 0.143, which means they're, yes, independent. Okay. Okay, so let's do the same thing for the next one. Are avocados and frozen independent? So let's use probability of A intersection B is equal to the probability of A times the probability of B. Okay. Let's have A be avocados and B be frozen. So what's the probability of both avocados and frozen? What number? 15 out of 140 is equal to, and then probability of just avocados? 24, right? We're looking at all avocados. 24 out of 140. And then the probability of just frozen. 90 over 140. And so then we need to test this. Well, 15 over 140 is 0.107. And if I multiply the two proportions on the right, I get 0.11. So what's the conclusion? They're dependent, right? They're not independent. So here, we always want to answer if it is independent or just not independent, okay? They're very specific, on that grading. So we'll make sure we use that terminology. So it'd say no, not independent.